In order to make the enthalpies easier to compare, we set some standard conditions for our chemical reactions. So if we are in the standard state, it means that we have if it is a pure gas, it's at exactly 1 atmosphere. If it's a solid or a liquid, it's the most stable form at exactly 1 atmosphere and a temperature that is typically 25 degrees Celsius. And if we're in solution, it is a concentration of 1 molar. And again, this is to make things easier to compare. Standard enthalpy change, which is denoted by the little degree sign, is when all of our reactants and products are in their standard state. If we have 1 mole of a pure compound that is from its constituent elements, so it's made out of the elements, that is the standard enthalpy of formation. And the standard enthalpy of formation is represented by putting a little subscript F at the bottom as a subscript and the standard as a superscript. And again, this is when we have a chemical reaction made from 1 mole of pure compound from its constituent elements. And this is a definition, so we're forming 1 mole. What this means is that sometimes our reactants are going to have odd coefficients. If we have the standard enthalpy of formation of a pure element in its standard state, it is going to be 0 kilojoules per mole. So the elemental form is 0 kilojoules by mole, and this is a definition. So if you ever want to find out what the standard state is, we look for compounds, or we look for the elements that have 0 kilojoules per mole. There are tables of standard enthalpies of formation that can be used in order to do calculations. And again, if we want to find the elemental form, we look for where they are equal to 0. So where our standard enthalpies of formation are 0. Now this isn't too hard to guess for hydrogen and nitrogen, but if we look at sulfur, so we have S8, remember sulfur is polyatomic, it's in the solid phase, and this rhombic, this is a way the atoms are arranged in their structure. So there's 2 different ways we can arrange them. The rhombic is the standard state. If it's monoclinic, then that is not the standard state. So don't let that throw you, the rhombic part. It's not essential for solving the problem. It's just a way that we denote the proper elemental form. So when we're writing formation reactions, say for carbon monoxide, we want to make it out of the elements. So our elements are carbon and oxygen, and we're going to use those as the reactants in our chemical reaction. They have to be in their standard state, so that means that carbon comes in lots of forms, but our standard state is graphite. Oxygen is going to be the diatomic gas. This presents a little bit of a problem because our definition for formation reactions is that we have to make 1 mole of the product. So our CO is what we need on the product side, but now that we've used the diatomic gas, we cannot balance this chemical reaction. So we need to add a coefficient in front of our oxygen so that we produce 1 mole of the product. Because we only need 1 oxygen, the coefficient in front of the diatomic oxygen is going to be 1/2. And so we do end up, when we're talking about our standard enthalpy of formation reactions with sometimes strange coefficients. See if you can write the standard formation reactions for the following compounds. Pause the video and try writing the reactions. So for carbon, we just saw that the elemental form was solid graphite form of carbon. For oxygen, it's a diatomic gas, and we're forming carbon dioxide gas. Now, we know that these are the elemental forms by looking back at our table and finding the row that is 0 for carbon and for oxygen with a standard enthalpy of formation of 0. So if we try and balance this, we've got 1 carbon and 2 oxygen. So this is our balanced formation reaction. If we try our aluminum sulfate, the standard elemental form of aluminum is just the solid form of aluminum. For sulfur, it is S8 as a solid in the rhombic form. And again, that is just how the atoms are attached to each other. We also have to include oxygen, which is O2 gas, to form 1 mole of our aluminum sulfate. Now we have to balance our reaction. Because we can only have 1 mole of the product, we have to balance the reactant side. So we have 2 aluminums, so that is pretty easy to balance. We put a 2 in front of our aluminum. If we look at our oxygen, we have 4 times 3, which is 12. Because it's diatomic, that means we need 6 oxygen. Now when it comes to the sulfur, we have 3 sulfur on the product side. In order to get 3 sulfur on the reactant side, we need to have 3/8 of our S8. Because we have 8 S's attached to each other, we only need part of that, which would be 3/8 to result in 3 sulfur on the product side. So this is just the way that we balance it, and we do end up with an odd coefficient for this particular formation reaction.